All right, now we'll talk about or statements. So the probability of the event A or the event B happening. Now what this means in math, this is very important. The word or specifically means A or B or both A and B, okay? So the probability of A or B turns out to be this here, probability of A plus the probability of B minus the probability of A and B. Now this can kind of be confusing as to why this is the formula. Let me talk a little bit about it. The probability of A or B, I'm going to use Venn diagrams to indicate this, what's going on here. So we can think of events as circles, essentially, and say, this could be event A on the left and event B on the right. And inside here, it would be A and B, okay? And if we're talking about A or B, we're just saying everything that's included in this whole thing. And so if I do probability of A, okay, this thing right here, then, well, that's just this whole circle for A, okay? And then the probability of B, that's this whole circle here. So you'll notice if I add those two probabilities, I've actually counted this area here twice. And so what we do then is we say, well, since I counted it twice, I don't want to count it twice, so I need to subtract one of it off. Okay, and so by subtracting one of it off, we'll just be counting it once. So let's do an example. We flip a coin and we roll a die. What is the probability of getting a head on the coin or a 6 on the die? So, probability of heads or 6. All right, so this is an or, so we know this is the probability of heads, plus the probability of a 6 on the die, minus the probability of a heads and a 6. Okay, so probability of flipping a heads, there's one way to flip a heads and 2 ways to flip a coin. Plus the probability of rolling a 6, well, there's one way to get a 6 and 6 ways to roll. And then minus, and here we have an and. So we're going to have to use our formula for and. Now, flipping a heads and rolling a 6 are completely independent events because the flip of a coin is not going to affect the roll of a die. And so the probability of heads and heads on the coin and 6 on the die is going to be the probability of heads times the probability of a 6. So that's 1/2 times 1/6. Okay, so now we need to simplify. We're going to get a common denominator here of 12. So this is 6 out of 12 plus 2 out of 12 minus 1 out of 12. And that is 7/12. Let's look at another example. Suppose we draw one card from a standard deck. What is the probability that we get a queen or a king? All right, probability of a queen or a king. I'll just abbreviate those as Q and K. So because this is an or statement, we use our or formula. Probability of a queen plus the probability of a king minus the probability of a queen and a king. All right, well, for the probability of drawing a queen, there are 4 queens in the deck and 52 possible ways to draw a card. Plus, for drawing a king, there are 4 kings in the deck and 52 total cards. Minus, and now the probability of queen and king. If I draw one card, what's the probability that that card is both a queen and a king? Well, it's obviously 0, right? There's 0 ways that we can draw one card and end up with both a king and a queen. So 0 out of 52. All right, so this is 8 out of 52, or 2 out of 13. Suppose we draw one card from a standard deck. What is the probability that we get a red card or a king? So probability of a red or a king. Our OR formula says this is the probability of a red card plus the probability of a king minus the probability of a red card and a king. Okay. Probability of a red card. We've got our hearts and our diamonds. Okay, that's 26 total cards that are red. So 26 out of 52 plus the probability of drawing a king. There are 4 kings out of the 52. And then minus probability of red and king. Now, I'll make a little comment here. These are independent events, and so I could use my AND formula. However, I could actually just use my basic probability formula here, which is how many ways can I draw a card that is both red and a king? Well, there are 2 of those. So there's 2 ways to draw a card that is both red and king out of the 52 possibilities. Okay. Now, I didn't absolutely have to do that. I didn't have to go through and just use the definition. I could have used the rule for independent events. Okay, now I can go ahead and combine all of these. So I've got 26 plus 4 is 30 minus 2, which is 28. 28 out of 52. And I can go ahead and simplify this. This is 7 out of 13. In your drawer, you have 10 pairs of socks, 6 of which are white, and 7 t-shirts, 3 of which are white. If you reach in and randomly grab a pair of socks and a t-shirt, what is the probability at least one of them is white? So this is the probability of ending up with white socks or with a white t-shirt. Okay, so this is an OR. So this is going to be the probability of ending up with white socks plus the probability of ending up with a white t-shirt minus the probability that you have white socks and a white t-shirt. All right, so the probability of white socks. I've got 6 ways to pick a pair of white socks out of 10 total ways to pick a pair of socks. Plus probability of white t-shirt. There are 3 ways to pick a white t-shirt out of the 7 white t-shirts which I have. Minus now the probability of white socks and white t-shirt. So these are independent events. So this is just the product of the 2. So the probability of white socks was 6 out of 10 times the probability of white t-shirt, which is 3 out of 7. So now we can get a common denominator. Let's go ahead and do our common denominator of, it's actually be 35 here. So this is 3/5 or 21 out of 35 plus 15 out of 35. And then minus, this is 9 out of 35. All right, so 21 plus 15 is 36, minus 9 is 27 out of 35. Sometimes our outcomes are organized in a table like this, and so we need to be comfortable using those. So here we've got some survey subjects, and they indicated whether or not they have received a speeding ticket and if they have a red car or not. So let's do this first one. We want to find the probability that a randomly chosen person has a red car and got a speeding ticket. So this is an AND. So the probability of a red car and a ticket. Okay. We need to know what to use here. Now, this is an AND, which means we need to ask ourselves, are these independent events? And we don't actually know. We can't just tell right off the bat whether or not having a red car and getting a speeding ticket are independent. And so what we're going to have to do is just look at the number of ways that this happened. And that's just this one spot here in the table. Okay, this is the spot. We know that 15 people had a red car and received a speeding ticket. And so that's 15 out of our total, and our total is over here, 665. And we can simplify just this down to 3 out of 133. If you want, you can write it as a decimal, and so this would be 0.023 approximately. Okay, for our next one, we want to know the probability that I have a red car or got a speeding ticket. So, probability of red or ticket. Okay, now this is true. This rule will always work, no matter if we have independent events or not. So this is the probability of a red car plus the probability of receiving a speeding ticket, and then minus the probability of red car and a speeding ticket. Okay, so for the probability of a red car, let's go back to our table. We just look at our row for red car, and our total for red car is this spot right here. So there's 150 total people that had a red car. So 150 out of the 665 total people. Plus, and then we have the probability of a ticket. So we look at our column for a speeding ticket and go down to our total, and that's 60. So the probability there is 60 out of 665. And then minus the probability of red car and a speeding ticket, which is the one that we previously calculated. That was our 15 out of 665. Okay, and so now we combine these. So 150 plus 60 is 210, minus 15 is 195 out of 665. And this reduces to 39 out of 133.